we're going to do lecture 26, which develops the stuff that we didn't quite finish last time. But most important, I wanted to talk about the projective algebra of the idempotent and orthonormality projectors. Well, a 2x2 matrix, but the theory is general. And then we'll take a look at a coupled oscillator described by a 2x2 matrix that requires the eigensolutions that this so elegantly gives. But this particular example will be a symmetric one, so the answer is fairly easy. And then we'll go on to an asymmetric type symmetry to get used to the what I call the ABCD method for dealing with two-state quantum systems, but also classical two-dimensional oscillators. That is the beginning of stuff that's in the Unit 6 that has to do with rotational mechanics, and the procedure for dealing with it is a symmetry one. Surprise for this room. The symmetry in this case is the unitary group in 2 dimensions, which maps in a 2-to-1 fashion with rotation in the space that we're used to, which is a 3-dimensional orthogonal space. So that is going to be the subject of the lecture 26. In any case, I'm going to go ahead here. What we considered last time was resonance, and we'll come back to discuss that. Now, what we did also last time was develop Hamiltonian Lagrangian matrix equations for these coupled oscillators, a symmetrization procedure that's somewhat weird, and then the actual equations of motion and their idea of finding eigenvectors geometrically by looking at the potential. And the potential is an elliptical hyperboloid, really, but the contour lines are all elliptical if the oscillator is harmonic. And the eigenvectors are found in between the directions in which the gradient is directed toward the center, where the force is directed toward the center of the oscillator. The result will be a simple linear motion, either along in this case, a fast mode with very tight contour lines, or a slow mode that goes back and forth between the contours that are intersecting this particular direction that has less slope, less force. So that's a geometrical procedure. Now the algebraic procedure, we talked about how you needed to have a secular equation, and simple solving this by Cramer's inversion yields you the null and trivial solution to an eigenvector equation. And we also at the very end began to discuss the application of the secular equation. In this case, it was a very simple equation, epsilon squared minus the trace of the matrix. The trace of the matrix is 6 in this case, and plus the determinant of this matrix. The determinant of our favorite matrix here is 4 times 2 is 8, minus 3 times 1, that's 5. So this is the equation for the eigenvalues of this matrix. And there's a general equation that for n by n is written over on the other side of the room there, and we'll discuss that a little bit later on. But it's really quite simple. In general, the terms that you'll find in the coefficients of the secular equation will be sums of what are known as diagonal k by k minors. You simply strike out the diagonal elements. You take them down one by one and leave yourself with a k by k minor. Now, it starts with the determinant at the very end of the secular equation. That's the constant term. At the other end is the diagonal one by one minors, namely the trace of the matrix. All of these things minus 1 to the kth power, in this case k with 1, so we have a negative sign in front of the trace. So the next one would be, if there were a bigger, let me say a 3 by 3 matrix, the next one would be 2 by 2 minors. And we'll talk about that later on, but that's an important thing to know, and also to have a way to program it, because obviously these are things that you would do for larger matrices in general on a computer. Now, the Hamilton-Cayley equation is a very interesting sort of thing. The secular equation is an algebraic equation, so by the fundamental theorem of algebra, it has to have n factors and n eigenvalues. Some of them may be the same in the case of very specialized matrices, but as I said before, if you take random numbers and stick it in a matrix, all the eigenvalues are highly probable to be different. And that's the assumption we're going to make just going into the beginning of this discussion, is that our secular equation has, in general, n distinct roots. In this case, it has 2 distinct roots. A very nice thing about the 1, 2, 3, 4 matrix is it's 1 and 5 are the eigenvalues of this secular equation. And if you stick the matrix in for the eigenvalues, the epsilons, if you replace those with the matrix, you replace the original equation or else the factored equation by the matrix, and the constant terms by the constant times the unit matrix, then that equation is always satisfied, no matter how pathological the eigenvalue situation might be. And pathology comes when you have degeneracy. So the numerical aspects of the matrix become weird as you become degenerate, but if you have degeneracy, usually that's a symmetry, so some other methods take over for you when that situation arises. In any case, with a matrix that you know can be diagonalized, this is not a problem. That this Hamilton-Cayley equation is a fairly obvious thing, but proving it in general is not an easy job. I have not found a really simple proof of this amazing result.
So what are the complications which would arise if we have degeneracy?
If you have degeneracy, then it is possible that this matrix is not diagonalizable. That's a pathology as far as physicists are concerned. So we'll give some examples of that. But it's not guaranteed.
Yeah,
it's not guaranteed. We'll prove a very rock bottom criteria for having a diagonalizable matrix. That will come. It's hard to state it now. We need to go into the projection business a little bit further. But once you have that, that's much better than what you normally hear. You normally hear, oh, it's normal matrices that are diagonalized. They have to commute with their conjugate. That's not an if and only if. What I'm going to tell you is an if and only if.
Because if, say for example, if I have a 3 by 3 matrix, so once we calculate the eigenvalues by solving the characteristic equation,
if they're all different, you're guaranteed that that matrix is diagonalized.
Oh yeah, so my question was, if it so happens that 2 eigenvalues are degenerate,
okay.
So I have got lambda 1, lambda 2. Then,
okay.
So in that case, should I be careful, like, is it not possible for me to just write a matrix with lambda 1, and lambda 2?
No, because that matrix may, in fact, not actually have 2 eigenvectors for these 2 eigenvalues. it may have what we call a nullity space. And that's what we have to describe using a language we're going to develop here.
Oh, okay. So which means if I have to diagonalize that matrix, then I need to construct a matrix U with the eigenvectors of the 3 eigenvalues and then perform.
That's a primitive way to do it. We're going to have a better way to do
Okay.
it. Okay. We're going to make the projectors directly. Okay. Then we'll see that what you're aiming at is true, but this is I say, a more powerful way to go at this problem. The other reason for going after it by projectors, which I just sort of mentioned a little bit about in our discussion, is that when it comes to analyzing symmetries, this is the way to do it. There isn't any other good way to do that. To avoid the part of group theory that everyone, including Schrodinger and Feynman, hated, you need this. This makes it cool. Okay? This is a bridge to the symmetry analysis. Okay? So, I put in green here the assumption that distinct eigenvalues will be considered until stated otherwise. So what you do is, having obtained your eigenvalues by factoring the secular equation, you immediately write the secular equation as a bunch of factors. Then you proceed to one by one, to replace each of these factors by the unit matrix. In other words, you just throw them away completely and leave yourself with a polynomial of degree n minus 1 if we had an n by n to start with. So obviously the first one to go, and these all commute with each other, so it doesn't make any difference which ones you put. But you might as well number them by the factor that you threw away. So I threw away the first factor here, so I'll call that little p1. And I throw away the second factor here, I'll call that little p2, and so forth all the way through. In this case, we only have 2 possibilities. Here's the first one, which I call p1. And it has to do with throwing away the eigenvalue 1, the projector or factor associated with eigenvalue 1. And then I predict, which has the eigenvectors associated with that eigenvalue of this matrix, 1, 2, 3, 4. They're just sitting there in the columns. Okay? That's what makes this powerful, is you get that thing virtually immediately. Especially for small matrices. In this case, it's a one-liner. And then the next one, where I threw away the second factor, I call that P2. That's the factor associated with the eigenvalue of 5 in this case. Then when I do that, that's just the matrix minus the unit operator times 1. So I'm subtracting 1 here in this case. Here, what I'm doing is subtracting the eigenvalue of 5 from the diagonal to make that matrix, you see. So when it comes time for you to do 2 by 2 matrices on an exam, this is almost instantaneous. But there's more to it. There's much more to it. Once you get these things, they have amazing properties. The projection operators. They are projection operators. What does that mean? Most people really don't learn what that really means and how powerful that is. But let's see why that works first, because that's the key to all of this. Each pk contains eigenbrackets. Now, why is that? Well, let's just put back the factor we took out. In this case, it would have been m minus epsilon 1, m minus the first eigenvalue times the unit operator. So let's put back the kth factor to make it with pk. That's the one we took out to make pk. So now what you have is the entire Hamilton-Cayley equation, which is 0 identically. Therefore, and you can put the part of this equation over on the other side, you see it's telling you that the matrix times that pk is going to give back pk multiplied by the eigenvalue. And not only that, since these factors always commute, a matrix commutes with itself, that's for sure, but a matrix commutes with identity always. So everything in here commutes with everything in there, so I can write it backwards. You see, I can put this thing on the other side, and so that means that this P times M going the other way, which at first doesn't look like it's going to be equal, because this matrix isn't symmetric, 1, 2, 3, 4, but it always will be. This is always true because of that super commutation I talked about. So this is telling me that M times the P gives me the P multiplied by the eigenvalues, but what that means is that I'm going to be working on the columns of this matrix when I operate from the left-hand side. So the left-hand eigenvectors are going to be the columns of the pk. And then, turning it around, this matrix would be operating on the rows of the pk and giving back pk times the eigenvalue. So therefore, the rows of the projector contain the bra, or right, eigenvectors of the thing. Up to a factor. We have to get that factor still. We have to decide what kind of normalization do you like. This lets you choose from a number of possibilities, which makes it powerful for other uses. But in any case, here's the basic idea for this 1, 2, 3, 4 matrix, is that this 1, 2, 3, 4 times this projector gives me back this projector times an eigenvalue. So if I just throw away the second column there, I've got an eigenvector equation written out numerically, and the eigenvalue is 1. Then P2 similarly. And you'll notice that the columns are proportional to each other. Here by a factor of -1, here by a factor of 3. The same with the rows. The rows are always proportional to each other in a situation that involves a 2 by 2 matrix. In a bigger matrix, they'll be linearly dependent, very much linearly dependent in the case of this assumption. But we're going to take care of that automatically. Okay, so this is the main message of this first rather dense slide, is first notice that the P's commute with M, give eigenoperators, you might say. These things are all matrices that are being written in bold-face here, but with the eigenvalues that make up that set of numbers that describe eigensolutions for this matrix. Okay? So, what we need to do is look at what we call idempotent projectors. Not just these things are sort of baby projectors. They're using lowercase p's to note them. The uppercase thing is a projector that is something called idempotent. Any operator is called idempotent if when you multiply it by itself, you give the self back again. These matrices that we have just produced have that property if scaled properly. So once we've got that down, then we can play some really nice games with the operator sets that we have here. And this will let us do what we call a spectral decomposition of an operator, or P operator expansions. So the real thing in here first is to see how the projectors make complete sets of eigensolutions that have convenient properties. So here's the deal written out in algebraic terms, and then here's the example. We'll keep doing it that way. Here's formal stuff, and there's an example. What we have just said is that the idea being that if I put matrix M here, when it hits pk, it gives me the pk with the eigenvalue epsilon multiplied. So what if we multiply projectors together? What if I put the pj projector here and multiply on the pk projector? So here's pj hitting this thing. Now this is the product symbol for a product over all, and it's pretty hard to see this, but I'll read it. M not equal to k, all over all M not equal to k. Remember, we took one factor out, so that kth factor that's been taken out is not going to be used. Its eigenvalues epsilon m are only going to be used for the other factors. So this is a product over all the epsilon m, the eigenvalues m, except the kth one that belongs to that particular operator that's being multiplied here by the jth one. The jth one misses the jth eigenvalue. Okay, so this pj times m, we already know what happens to that. That just gives me an epsilon j pj. Okay, so here's the pj multiplied by another factor. And this is the idea of this. This one is without a k, so this is all m except k, and this is all m except j. Now if j and k are not equal, then I will have reconstructed, by putting these two back together again, I will contain within the construction the Hamilton-Cayley equation. That is, I will contain all the factors I need to make 0. So if j is not equal to k within this product, it will automatically give 0. And you can see that by looking at P1 times P2 here. This row here multiplied by that column gives me 0. This row multiplied by that row gives me 0, 0, 0. I get a big 0 from any product of different little projectors, baby projectors. Okay, we just have baby projectors. Well, we need adult projectors, and to make an adult projector, we got to divide by this factor, which is not 0. This is for all m not equal to k. So this is a factor that is definitely not 0, that will be multiplying when I take pk with pk. I will get pk back again, but this time it won't be multiplied by something that's 0. This will be non-zero. By definition, no degeneracies here. Okay? So that's the hardest part of the logic right there. We're going to make use of that to build something quite elegant. So we're going to make an adult idempotent, is the word for adult in this algebra discussion. We're going to make an uppercase pk is equal to lowercase pk divided by this factor, the product over all, and this is pk, over all epsilon k belonging to the one we're interested in, minus epsilon m for all the m except for the k, the one that would make this thing blow up. So there, again, that's why we don't want degeneracy at this stage, because I will run into something, if they're degenerate, that gives us 0, and that projector will be useless. Okay, so here's pk written out again, the little pk. It's the product over all m not equal to k of the matrix minus the mth eigenvalue times the unit operator. Okay? So let's look at our example. I'm interested in the adult projector, the idempotent projector, P1. That's 1 minus the other eigenvalue that's not equal to that. There's only 1, so I got 1 minus 5 here. That's a minus 4. Okay? So that's going to take this thing, which has minuses on a diagonal and is positive off diagonal, and turn it into the same thing divided by 1/4. Okay? And then this one right here, that's this thing, okay, divided by 5 minus 1, which is 4, so I just divide by 4 and put a sign on that one. So there are your projection out there. Now, what are the properties? Well, first, I didn't do anything by putting factors on these things that would change this equation. So these things are still orthogonal. This row here times that column is 0. Now, this row here is a bra. That's a scalar product with a ket from another eigenvalue. We're already getting orthogonality from this thing, but now we're making it so that when I multiply this by itself, I get something that is going to be, well, almost, it's not quite there yet, orthonormal. So this sums it up, okay? Now actually this is sort of a typo right here. I should have put uppercase P here to emphasize that now we're dealing with the adults. But that certainly, I think, goes without saying. We just multiply both sides of this equation by a coefficient products like that. Okay? So now let's look again at this one. This is something that you can do fairly easily. And this relates this whole discussion to the more commonly used in modern quantum mechanics, including Feynman, Dirac notation, in which you use this, you use this little symbol here sometimes. That's the mathematical symbol for an outer product. But basically, you make this matrix by taking the thing that we had before, 1 and minus 3, and dividing by the square root of the coefficient that sits on the diagonal there. You do a similar thing with this matrix. Now we're going to discuss all that later, but it's ought to show you that we're going to be getting the Dirac expression for a projection operator by simply factoring these things. And that factoring can be done in an orderly way. I'm just sort of showing it to you right here. But these right here are the vectors that we're actually going to call our bras and kets. This one being a bra, that would be that thing right there. Then circle cross product, that's the point to point in Dirac's notation, with a ket, which is a column, you see, and that is this vector right here. And you can see 1/2 times 3/2 gives me a 3/4. 1/2 times 1/2 gives me a 1/4. That takes care of the row. Then I go down here and you do this row with this number here. This is 1/2 times 3/2, that's 3/4 again. And then here we go, 1/2 times 1 is 1/4 again. Okay? And each of these has that. The sign is correct for this one. And you can check that that's indeed right. The question is, how do you do this elegantly in a more complicated situation? We'll talk about that later on. But I think you'll get the answer to how we do that by simply looking at the fact that when I multiply these two together, like I was doing there, I am taking a scalar product. So the projection operator already contains all of the scalar products with the right normalization hiding in them twice. And you just simply have to separate that to get this. But let's get a little bit of the geometry that we're making here and show what it means to be mutually orthonormal. What we have here are bras and kets, covariant and contravariant. Say covariant is the columns that are the kets that we talk so much about with regard to GCC, and the bras are the rows. They're the contravariants, if you like. We're not going to use up and down index notation. We don't have to. We avoid that nonsense, very much nonsense for this, because this is so elegant. Anyway, if you just look at the projectors that you've gotten here, say take that column there and plot it, that's the ket number 2, okay, 1/2, 1/2, saying this graph here is 1/2 units, there she is, okay? And then this one right here is 3/2, 1/2, that's coming off of the bra, which is that thing, okay? So if you plot that, it's over here. So you see right away the same thing happened with the covariant versus contravariance. The covariant guy is not in the same direction as the contravariant guy. And that's what you're going to get whenever your matrix doesn't have a Hermitian or just plain symmetric shape. That is, when the off-diagonal elements are not equal to each other throughout the matrix, you're going to get that situation of having something different for the bras than the kets in each of the eigen cases. Then as we go look at these guys, this guy right here, that's the number 2 ket. Here's a number 1 ket right there. We go down and plot those things, okay? There's the first one right there, 1/2 minus 1/2. And there's the second one, 1/2, let's see, that's the first one right there. Yes, this is the first one right here, 1/2 minus 3/2, and then the second one is this guy right here. let's see if I'm looking at the right thing. There's the bra, there's the kit, and there's the kit right there. So those are the two. They're not in the same direction either. But the one contravariant is perpendicular to the two covariant, and vice versa. The two contravariant is perpendicular to the one covariant. Okay? Now that was automatic from this point on. That's just the secular equation becoming Hamilton becoming zero. The Hamilton-Cayley theorem giving us zero. Okay? But this other fancy stuff we're doing with normalization is what's really elegant about this. The idea is to work with operator normalizations, because then I don't have to play with square roots. To make the vectors, I have to play with square roots because I'm ripping the operator apart, and the smoke that arises from that bisection, that surgery, involves square roots. Doing this, and what we're going to do here, doesn't ask you to do that, and that's what makes it powerful. It's something that you can work on operators with. You can do it at the operator level. Okay? So these PGA have a mutually orthonormal bra-ket vectors inside of these idempotent projectors. Okay, now here's something that's really cool. And this at first is really hard to prove in general. Now it's easy to see if I take these two projectors that I've produced here, these two matrices, and add them up. 1/4 plus 3/4 is 1. This one is a minus a quarter, it's a plus a quarter, cancel. Same with that one, even though it's not symmetric, because this one's minus a quarter and it's plus 3/4. Okay? And then finally the last one, also 1. 3/4 here plus 1/4 there. Okay? This will always happen in the situation we're talking about. So what we've done is very elegantly lay out orthonormality versus completeness. But in this case, this way of doing it, this is really different looking than this. Whereas when you do functional analysis, one of them's 6 and the other one's half a dozen. They look very similar. I'll make that point later. But this is really different. This is really cool. The fact that I get 1 by adding these things up, in general, is, well, if there is a God, a mathematical God, he's made a gift here. Okay, now let's look at this using the functional analysis language that you learned using Dirac notation, but also the old-fashioned psi notation. Okay, orthonormality of, say, x and y. Okay, whatever that is. Okay, it could be actual x and y coordinates, or it could be just some vector that you picked arbitrarily. 1 and 2, similarly, some vector that came out of one of our calculations or whatever. Okay, the idea is that when you're doing quantum mechanics, you always have this as an axiom. So really, that's what it is. And Feynman was honest about this. He said, okay, we're going to have axioms of orthonormality, we're going to have axioms of completeness. Okay? And he gave a physical reason for that. That's what's so powerful about Feynman Volume 3, is it attacks this mathematical enigma with physics. It says this is what happens with beam experiments and filters and things like that. That's great. But right now we're doing just the mathematics and trying to look at the physics notation and see what it says. And the idea is that this sum here is sums of ket bras, right? We've already noted that the ket bra, knuckle to knuckle, is an idempotent projector. And with that notation, it's fairly obvious that we get this kind of relationship. Because if it's a ket 1 bra 2 and I multiply that by itself, the bra that's the 2 hits the ket that's 1 and annihilates it down. So you get a 0 when they're not equal. And the Dirac notation is fairly elegant for showing that. But the Dirac notation has this thing about saying that 1 is the sum of these, so you can stick a 1 in between these two vectors, and there you get an expansion of things that may not be 0. In fact, they usually aren't. So this is a vector tensor analysis sort of way of looking at the thing using Dirac notation at an orthogonality relation. Okay, but let's put the 2's under the 1 and 2's under the microscopes. Okay, we have a relation between them that's supposedly that way as well. You see, so I stick a 1 between them, and that 1 can be a sum of xx and yy ket bra, and that's called completeness, right? Okay, now it really looks like that when you put wave functions on these things. This thing right here means psi sub 1 x function. This one means psi sub 1 y function of y star, because it's backwards. The y and x coordinates should be on the left-hand side by conventions for wave functions. Okay? So this is telling me I'll get a delta function xy, and this will be a Dirac delta function. That is, it'll be something in a Banach space, which is completely different from the Hilbert space you normally work on with finite quantum mechanics, discrete quantum mechanics. This is continuous quantum mechanics, but it's a sum, you see, over 1, 1, 2, 2, and then all of the different things. That's the thing that's making this. Well, that looks to me like a completeness relation. This is the orthonormality relation down here, you see? So whenever you have two spaces that see each other, a completeness relation in one is an orthonormality relation in the other. You see, and normally this sum here, x, x, y, y, would be an integral if it was a continuum, x and y. So you see, this is very confusing stuff. This is simple.
I just have one mathematical question.
Yes.
X, ket x is a vector in a continuous space.
A continuous space, that's
but
right.
Whereas I and j are vectors in a discrete space. So is it possible to take the inner product between two vectors, one belonging to a continuous space and one belonging to a...
Yes. And you have to ask, and this is something I always tell when we're doing mathematical physics, I always say, okay, the way to understand mathematical physics, difficult concepts, and this is an advantage you have that the creators like Hilbert and all those guys didn't have, and that is to say, how am I going to get this sucker on a computer, right? I don't have a continuum of memory, right? I have a discrete set. Now, I may have gigabytes, but it's still finite and discrete, right? So when I talk about a vector like x, I imagine that my memory is keeping track. I also imagine I have a pen, and that's the trouble with whiteboards, is everything dries up. I used to say that any institution, you can tell the quality of it by the ratio of whiteboards to blackboards. If that ratio is high, it's stupid. If it's blackboards or a lot of blackboards compared to whiteboards, it's a smart place. Okay, so you can see we got this much whiteboard and we got a lot of black over here, so we're in good shape. But anyway, I hope this one isn't dry. I would say that I had an x, 100. Okay. Well, let's just say x number 3. Okay. So I've got memory here, memory here, memory here, memory here. Nothing's in the memories yet, just zeros. But x3 would be equal to the third dot here with a 1 in it. Okay? That's a continuum seen in a computer. Okay? So you have to look at all of these functions and kets and bras. For instance, down here, if we're talking about a psi I, we're talking about an I. Well, that thing, if I'm talking about that wave function, psi uh, say, whatever number, it doesn't matter, A, okay? What I'm talking about is filling that particular ket A with numbers, okay? Whatever these are, you see. So I'm going to have here the amplitude to be at the x point 1, psi A, okay? I'm going to erase that one. I'm going to replace it with something besides 0. That would be psi 2 of A, you see? And in this memory, I'm going to put 3 of A, okay? And so on, all the way through, you know, a million memories, right? And I will have a function, you know, tabulated for me, and you could start plotting a curve here, you see, you know, against this thing, but these would just be discrete points, you see. I wouldn't have anything in between them, you see. So that's the idea. You got to get that idea in your head, because that's the way you're going to do most of your calculations of functional analysis in any kind of situation where you're using a computer to solve differential equations, partial differential equations, right? You're going to have memory stacked like this is going to be worked on, stored first and then worked on by the computer. So when you go to say, well, can I make an outer product of this? Yes, you can. You have another set of memory lined up like this, which makes a matrix, right? The computer's going to go and make the products of every one of these with every one of these and lay it out in a great big n squared. That would be a million times a million, which is pretty large. You're going to have a trillion memories. You need a terabyte to do that. Okay? Assuming you have 1 byte memory, which is pretty low, so you need a lot more than a terabyte. But we're going to have that. We're going to have exabytes and you know, how far can you go on this table here, okay? Up there I can only go to exa because that's 18. I don't even know what the next one is. But we'll be hitting that one someday, maybe, before you guys are dead. That's the game we're playing, and it's a nice game in the sense that, boy, I couldn't ever get half the things I need to get done without all of that power. Okay, so far so good. Now, let's do some other things here. Spectral decomposition. That's really cool. It's based on this, the completeness relation. And the way it works is you say, okay, I've got this equation here that tells me that the matrix times the projector is equal eigenvalue times projector. That's kind of what we came in doing up here. And there it is. I finally corrected the typo. There's the result, of course, because it's eigenvalues. Okay? Well, what you've done is you spectrally decomposed the matrix. That's really powerful. Here's 1, 2, 3, 4 written as 1 times P1 plus 5 times P2. That's 1 times this guy, who's this guy, and 5 times this guy, who is that guy. Okay, that comes out to be the matrix. Okay, but separately, it's really powerful. Suppose somebody wants to give you a function of that matrix. This is what you need to do. Suppose I need to multiply this matrix by itself 50 times. That's your homework, right? Go start multiplying 50 times, right? No, you don't have to do that. You just go 1 to the 50th times the first projector plus 5 to the 50th times the second. Do you see how that's working? Think about the algebra. Think of what it is you're doing here. You're taking this binomial and raising it to the 50th power. Okay? Now normally that would look like you'd have a heck of a lot of terms from that thing, but the only terms you're interested in are the diagonal terms where P1 hits P1. If P1 hits P2, it's 0. So out of that binomial, you're only interested in 1 times P1, P1, and then 5 times P2, P2, right? But they're idempotent. P1 times P1 is P1. P2 squared is P2. So, no matter what power I take of this thing, I simply have to take that power of this eigenvalue, multiply it by P1, take the power of the second eigenvalue, multiply it by P2. If I've got 3 dimensions, I've got to do this for each dimension, but that's it. Powerful. This is, you know, the whole idea of operator spectral decomposition is to make a child's play. Any sort of manipulations you have to do. Any function you want of this thing. If you want the square root, be my guest. You want the Bessel function of that matrix? Be my guest. You want the exponential of that matrix to do a Lorentz transformation? Be my guest. That's really cool. This really adds to your power to do things and to think about them. Now it's really powerful when you have a whole group of operators that you want to reduce. Perhaps they're commutative, abelian. They commute with each other. Then you do exactly this. Every one of the elements in that group is going to get this treatment of being a linear combination of projectors, so that any function of that thing that you want is just going to be a sum like that. You just have to know these eigennumbers. Those are called irreducible representations of the group operator. End of group theory. That's it. That's all you need to know. All the garbage that Wigner and Weil and stuff throws at you, that's just because they apparently weren't aware that this was was available. It's no longer a grouping pest, which is what Schrodinger called it. Okay, does that make sense? This is algebra that really makes. Now, we're going to take an example that is a symmetric matrix, has a determinant, this, a trace, that, 20 and 99. It's kind of a weird polynomial, but there's what I'm going to have to solve to get the eigenvalues of this spring matrix. Okay? Now, we're going to assume, this is the other part of this thing, idealization, that these are two masses that are equal. Okay? And the other thing we're going to do to make it symmetric is we're going to make these two springs on the end equal. So this is what I call a B-type matrix. I've already used that terminology, bilateral symmetry, that this has. Okay? That's what we're after here. So we got a 1 here for the coupling, and then we've got K1 plus K12. Remember how those two add up to make the diagonal term. And it's the same for both. 1 plus 9 is 10. So it's these eigenvalues that we're going to get. Now, the thing that you should be aware of is that the classical solution to this thing is a Newton's equation, which is a second derivative equation. And so the eigenvalues that we get here are the frequencies squared. That's just the old idea that K over M is equal to omega squared. M is 1 here, so we don't mention that. But that's actually the normal mode frequencies equation right there. So we're going to get a frequency, angular frequency, radians per second, for the number 1 of the square root of 9. That's 3 radians per second. And this will be square root of 11 radians per second for that. And then we want to check the projectors. Okay? They're particularly simple. With the 11 eigenvalues, say that's the one I want to call the first one. It's the highest frequency. Normally I would maybe put, let's see if I'm doing this right here, P1. Oh, yes, I am doing it right. I'm calling this one the first one. That's the lowest one. That's what most people count. But what I need in order to make the projector is the other one. Okay? I need the number 2 here, eigenvalue, 11. Okay? So 10 minus 11, 1. K12 is minus 1. Okay? There I go. Here's P2. Now I use the 9. Okay? Well, this one comes out really simple, and that's the thing that we're going to make use of without bothering to do the projector combinations. With symmetry, I can tell you right away, that's what you've got to get for the projected eigenvector projections for a B-type matrix. Okay. Now here is the projector factored. And you see, the thing that's funny here is I could play the game they play over in conjugate and covariant I could put the whole square root of 2 onto, I could put the whole factor 2 onto the ket,
Dr. Harter?
or the bra, either one.
Dr. Harter?
I'm splitting them equally. Yeah.
When you say a K-secular equation, is that the characteristic equation to calculate the eigenvalues? Of
This thing right here.
Yeah.
That, when you say characteristic equation, what you're doing is you're letting the eigen solutions characterize the matrix. That's the reason for that name. But I think a better name is secular. It goes back into the history, right, of, astronomy and versus the church, right?
Okay.
Yeah. Okay. So,
Oh,
yeah,
okay,
and
that's
it's
it.
shorter. Characteristic equation doesn't exactly roll off your tongue. Secular, right? Very good. All right. And of course, don't forget the Hamilton-Cayley. I call it the HC equation, Hamilton-Cayley equation, where you actually stick matrices in for the eigenvalues K here. Does that make sense? Okay. So here's this ket-bra outer product, and here's this ket-bra outer product. With this would be the normal thing that you would write down about this thing. And you see, you would have a unit vector in both cases. And of course, they've got to be orthogonal. So, what's the mixed mode dynamics that's associated with this? This is the most general state here. Okay, the general state will be a sum of these. This is basically just expanding the evolution operator for this system, an exponential of the Hamiltonian matrix, or I should say the spring matrix. Okay, so you're going to see a frequency associated with the slow mode, the one that goes up the 45-degree line. So this is what we were looking at last time. And this is the fast mode that's perpendicular to it, normal to it. That's why they're called normal modes for one time, I remind you again. Okay? And so there's a picture of the results, okay, that we had going on this screen before. I'll just go back to refresh your memory, and I'll take to start with, I'll go ahead and use a very slow beat. The beats are going to be very slow. So this one, you can hardly tell me those are ellipses in the potential there. It's very, has very low astigmatism. If you had a plot like that for your ocular eye exam, okay, they might not even give you glasses. But this is a astigmatism at 45 degrees, right? That we're talking about here, just like the one we did before. So what's happening here is very slowly they're getting out of kilter. These two frequencies are very nearly equal, so the beats take a long time. Okay. We started here and we're starting to build up, and the other one that didn't have anything, and the one that had something is losing. Okay? Now it's fun to look at that and just see what's going on physically. We'll come back to the mathematics in a minute here. But notice what's the phase relationship between these two phasors? 90 degrees difference, right? Remember that 90 degrees was that magic phase lag that was we call resonance in the single force damped harmonic oscillator. So this guy here, he's always 90 degrees ahead of this one. Now what does that mean physically? It means that he's got his velocity in phase with the force. That is, the force that he's applying there is in phase with the velocity of that creature or person. If this was a dance combo, this is the, say, the leader, the guy usually in the old days, not anymore, but let's say it is, says, "Come on, baby," and gives maximum force right there. It's crossing the origin. Then says, "Okay, now come on this way, baby." and maximum force right as she crosses coming toward me. And in doing so, he's putting energy in at the best he can do. And right now, kind of is the best because they're equal amplitudes now, and they're making a circle, or nearly a circle. Now the ellipse is going to be more higher. It's going to have a bigger axis on the upright, whereas before it's had a bigger axis on the horizontal. And you can see this phaser is smaller. But that 90 degrees is being maintained. It has to be maintained in order for the resonance to continue to feed the, in the direction that it was. This is the leader. And the leader gives to the follower. This is true when you have many phasers, and it's the way waves work. Always 90 degrees ahead of the follower. And that makes for an ellipse that is either horizontal, a circle, or vertical, you see. Now it got stopped there, so I'm going to start it over again with a little more speed so we can get through the thing in fairly good shape. So I'm going to run this thing a little faster. Come on, baby. Come on, baby. Just getting it going. You see, starting to get a phaser down there. Come on, baby. Come on. Now we're getting some. Now, the important thing to remember is that there's some conservation going on here. The area of these two, sum, is constant. That's equivalent to amplitude squared, sum, being a constant. That's the energy of a two-dimensional harmonic oscillator. In quantum mechanics, these are going to be the psi functions right here. And psi star psi of 1 plus psi star psi of 2 is the probability which sums to 1 if we're talking about something that we call, I hate to use the word particle. Anyway, we're going to maintain a 90 degrees all the way down to he's just got 1 or 2 pixels left, and then, boom, he's going to go out the back door. And now this is the leader. Now she's taking over the dance. Come on, man. Come on, man. Now go this way. Come on, man. Come on, man. Okay. Now she's losing her area to as a leader, and she's always 90 degrees ahead while this process goes in reverse. Okay. Now what we have to learn is that this is a process that goes on when you resonate a spin. The picture up there is a resonance of a spin. That's an NMR cycle that we're about to complete. Well, I should say we're about to complete halfway. We'll get into that later on because spinners in U2 have a 2-to-1 relation to the space that the vector lives in, that we live in. So that has to be discussed. And now finally, she's out of gas, and he takes over, and that's kind of where we came in, except it isn't quite, but we'll tell you that story later on. So as they say, the beat goes on. This is a 2-dimensional quantum system and only has one beat, one frequency that you actually observe and work with. These two frequencies can be MC squared and MC squared plus this. You can put your origin on here, in between the middle, and there. It doesn't change your results at all. The beat's what's important, the differences. And that's what's going to show up when we analyze this. What we're going to get here is this frequency number 1 multiplied by the eigenvector number 1. And whatever amplitude we started with, let's make that equal to that one, just for the sake of getting a thing to start at 0 in one place, the first component. And then here's the anti-symmetric vector, the high-speed one with a higher frequency, omega 2. And so let's collapse these, put them together, and what you see here is you're going to get, if I'm not mistaken here, when I do the sums of these things, I'm going to get the upstairs to be a cosine and the downstairs to be at least proportional to a sine. So I'm going to be seeing a e to the minus I omega t here plus, and then I'm going to see a difference down here. Now whenever you add two exponentials, this is the beat formula. I'll go ahead and put it up here on the board just to make it clear. We're going to use this. I used it in the lecture the other day. E to the I b added to e to the I a is going to be factored into e to the I a plus b over 2 multiplying e to the I a minus b over 2. Okay, that's the first term. That gives me this term right here. Okay, and then I'm going to add an additional e to the minus I of a minus b over 2 to that. Okay, and this one will then give you the b, a plus b minus a quantity a minus b gives me an e to the I b. All right? Now, if I were to do half the sum of those two, then I would have half the sum of those two. But that's recognizable, you see, as e to the I, this thing again, a plus b over 2, which is kind of the phase. And then this thing right here is simply the cosine of the quantity a minus b over 2. Okay, now these a's and b's have the time behavior, or and for a general wave, space behavior as well. So you're seeing that coming out right here. Always a minus sign on things that are going, this is left-handed, clockwise. These are all clockwise phasors being added here. Look at geometry of that a little bit too. But then anyhow, when you get this one, you get a cosine, which is what we're plotting there, and you get a sine down here, but with an I factor. Note the I phase factor that's on top of this phase, you see. Well, that little I there multiplies by pi over 2. It sets you back by pi over 2. So old number 2 here is set back by pi over 2. Unlike what we've got here, this one is set forward. So this is a leader. This one we've already gone through a cycle and stopped. But I go again on this, and you'll have a situation that's shown in the beginning of this resonance right here. Okay? And I'll just stop it, slow it down. It doesn't have a pause, unfortunately. Okay, there we are. Very paused, almost paused. Okay? So that's the situation. This one right here is I. That means it's been pushed this way. I'm sorry, been pushed this way back from there. This one pushed back 90 degrees is right there. That's the I. Okay? Does that make sense? So this is the anatomy of every resonance that happens. Every time something is feeding energy to something else in a high-quality oscillator system, this is what's going on. These are the beats. Now, as I said, if you have 3 frequencies, you've got 3 beats. If you've got n frequencies, you've got n times n minus 1 over 2 beats, all going on at once. That can be confusing. But if you just excite each pair in a quantum system, you get to see the beat associated with that pair. And through just doing that a few times, you get to feel, how does that system move? Those are its main, first few combinations are all that you have to worry about most of the time if you're not hitting it with high frequency, high Fourier components. Now this is a very quick discussion of the geometry of what we're doing here. Okay? This is what I call a visualization gauge. And what I mean that is, I'm allowed to set the origin for any of these frequencies. I'm going to just pause this for a moment here. I can set, for example, this set of phasors to be not moving. I'll just go to a gauge where whatever frequency they have has been subtracted, and I have to subtract that from this one so that they maintain their differences. Okay, so this could be two coupled pendulum, or it could be an optical electric field in a dichroic media that has a faster index of refraction this way than that way, or vice versa. Okay? So what we've done here is say I've got two oscillators. One oscillation, a normal mode that is in phase, and that would be this mode right here, roughly. I got a little too much on the top and the bottom, but that's the basic idea. That would be this mode right here, okay? Then this one is another mode, that's the normal mode to the first one. If this was the direction in polarization space, X and Y, that was the slow mode, then this would be the fast mode, using the simulation that we've got set up over there. And so that would correspond to this kind of motion. I'll set both of them as close as I can to 2. It's a little hard to do because everything's backwards up there. You've got to take that guy and put him on 2 and put this guy on 2. That's pretty good. So that's just a mode that is just going to go independent of whatever this one is doing. That's the whole thing about quantum mechanics. Is each one of these dances to its particular eigenfrequency. Eigen means own, its own frequency. Saying its own eigenfrequency is redundant. German for own, mine. Okay? So, I'm going to start both of these at once. That's what we're doing when we do the geometry over here. Okay? And let me go ahead and start that again. I'm going fairly slowly now. Okay? So what I've done is basically what I'll do, I'll just set this thing to 0 for a brief moment here. Okay, so there's the thing sitting there. But then what I do is I say, okay, I could start this slow mode if I wanted to. That set it off the side. So the slow mode would go at its frequency, which is really slow now because we've got things slowed down. Okay? Or, let me stop it right there. I could start on the high side here, or the low side of the fast mode. Okay? And then it would go on that one at its frequency. It's only very slightly different from the other one. Okay? So think of those as X and Y. Now what we're going to do is we're going to take a little bit of this and a little bit of that, or actually a lot of that. I'm going to take a vector that's this plus the other one. Plus the other one sets me over here, or say here. Now I've got both of them going. Okay? So that's the idea. I take the sum of this mode plus this mode, thinking of it as an arithmetic problem with just these two numbers. Okay? These cancel, so there's nothing here. It's all here. All of it's over in the whatever we would call the y-axis on the normal coordinates. And we're going to let it run. Okay? Now, if you just let it run a little bit, you see, what you're going to do, since we've said these two are fixed, this is the beat frequency. This one's going to go at the beat frequency. These both are going to go tick, 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 tick together, right? These are normal modes. They have both the same frequency attached to both of those coordinates there. Okay? So pretty soon, what we're going to see is this guy right here, this one, has ticked over to here, okay? Just as this one here is ticked over to there. That's this one, right? And we're going to get the sum of that and that, which is a little vector pointing this way. And this one's going to be a sum of this one having ticked over to here and that one, which is that one right there. So the sum of those two is this big long vector pointing out here. Notice how these two parallelograms have an equivalency, where this is the main diagonal that we call the half sum, and this is the half difference that we're getting over here on this arithmetic. So here's the half difference of those two vectors, here's the half sum. And they're always going to be orthogonal to each other as this thing ticks along. Okay? So we're letting these two rotate at the beat frequency. There's the actual clocking that I just tried to point out. And we're summing them individually, and now here I've let them go all the way to 1/6 of a period, okay? And now we're getting, so they're pretty close to equal, and finally, at 1/4 period, they are equal. That's what this is. At a quarter period, if this was optics, you would have taken your plane polarization and turned it into left circular. You've heard of that phrase, quarter wave plate and left circular, right? Think of all the things we're doing here at once. Polarization optics, quantum mechanics two-stage system, pendulums, junky old pendulum sitting here on a projector, right? Okay? And this continues, you see, until here, where you have what's called a half-wave plate. I've now turned X polarization into Y. And then it will continue to, going till I get to this one, where now the pi/2 is reversed, and I get right circular polarization. Now what we need to do, and we have only a little bit of 5 minutes or so to get started on that, is see how in the world do you really visualize what's going on here. This is the most visualizable of them all. This pendulum, yeah, sure, you can see the pendulum doing its thing, but we might call this localized and this flipped. That's indeed tunneling language. I literally start in one potential well and somehow dematerialize and rematerialize over in the other one. But the optics is, I think, much clearer. Well, light is the, as I said in the talk I gave on Friday, the one that gives us the clues. You shed light on something. Well, I mean a coherent shedding of light that makes coherence in your head if you follow it far enough. Okay? Now, before we go on, I would like to just mention there's an asymmetric case here, just to, obviously give you a problem that's more difficult than the one we just did, just to make sure that you can do something that's asymmetric. Now, usually I give nice even numbers when I'm doing tests and things. This one comes out with a nice determinant of 64, a trace of 20, even though it has square roots of 3's sitting in there. The secular equation, however, is very nice. It has a perfect square eigenvalues. That means when you take the square root of these eigenvalues, you will be getting integers, and that means you're going to get a closed trajectory. You won't get the big mess that we're seeing there. I've set those frequencies up to be golden ratios, so they're the least rational, and they don't make anything that people ask questions, embarrassing questions about in the middle of the class. They don't make patterns. This is sort of the opposite case here, as you'll see, because I've got a very nice ratio, very small fractional ratio of the things. So beats depend on the differences in these frequencies. That is, the difference in the square roots of these for classical oscillators. ratios are also important if you're going to characterize the whole trajectory, or the quantum system that's going to make a wave function that tries to somehow mimic that trajectory anyway, here's the first projector, which comes out to be that. There's the factoring, and factoring is very easy because you know that 3/4 square root is the thing. Square root of 3/2 is the thing that you need to pull out of it. Well, you just pull out of every one of them, and you'll get the direct product. You'll factor the thing into a Ketrov. And so that gives you the projection operators in a nice form. You don't have to use that form, but it's worthwhile sometimes to have that form. Because what you're going to do, see, you name me an initial vector somewhere in that plane, or some complex combination in that plane, some ellipse usually, some elliptical shape if it's polarization, and I apply 1 to it in order to solve the problem. I apply P1 plus P2 to that. Okay? In other words, I apply P1 times 1, 0, if that's the one I want. It could be anything. Complex numbers are allowed here. And then P2 times that same initial condition. We're using the same initial condition we just used in the previous example. So, what you're talking about here is square root of 3/2. That's projection on the number 1 axis. And here's the projection on number -1. It just comes out nice and automatically from the projector, either in that form or some other form. Doesn't matter how you write, you're eventually going to get these coordinates as your initial coordinates in 1 and 2. Okay? So what you get is this thing. Now, this is going to be the ellipse. That's your initial position, this much of that and this much of that. Okay, those are the normal coordinates of that particle at the time equals 0. That's what it looks like in x and y. This is what it looks like in that tip coordinate system. And you'll notice the coordinate system isn't perfectly between x and y. That's because this thing doesn't have equal diagonals. Okay? But it does make a Chebyshev polynomial. And this is really cool. Here's a bunch of sines and cosines, well, cosines and cosine with a phase, that's making a parabola, a perfect parabola. That is a perfect parabola. It's not a catenary or anything fancy like that. It's a parabola. It's the first non-trivial Chebyshev polynomial. Here's Mr. And they say that you can call him Chebyshev, 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 and, well, on and on. I mispronounced every one of those. But it's a famous guy that did all kinds of wonderful stuff. And this is the simplest non-trivial one that shows up with combination of sine and cosine. I have a frequency to ratio of 2. Okay, and that's the actual plot out of the time things, and you can, see that the beats going on in there are pretty fast. Now that's the other thing about this. This does not get any more difficult when you go to faster oscillators. Okay. Now I'm going to speed it up here because we're running out of time and video film. But here's one where they go back and forth pretty quickly. Let me go back and just start it again. This is the middle case here of a B-type oscillator. And you can see the beats are really quick. We just went through one, which I call a half beat, but we'll get into that factors of 2 later on. But you can see that, again, I've chosen something that's golden ratio, so I don't see patterns in here. This is an extreme pattern, and it will just repeat on that. That's totally periodic, very simply periodic. Okay, but let's go for the gold, so to speak. Let's go for something that's really fast. I'm getting beats as fast as the oscillation, or faster, some of it, right? This is really a lot of astigmatism for this potential. Okay, this is a lot faster than this. Okay, so everything really going like that. Doesn't change the mathematics at all. If this is a quantum system, quantum mechanics is linear to, as far as we can tell, any sort of extreme you can think of. And so I would, caution about that. I think that the computer has crashed, and so am I. We're over the time over a little bit, but that's really what I want to say. Now, the rest of this particular lecture will be the first part of the next one, and that is to make a connection between the two-stage Schrodinger equation, which is first order in time, and what we've been doing here, which is second order in time. And that's really an eye-opener for getting some feeling about how quantum mechanics and relativity, too, they are the same subject. This is one of the ways they get together. So let's call it a stop there. And you can ask your embarrassing questions with the camera turned off.